Okay, so today, we're going to start chapter 4 today. In my last class, we looked at all slides, so if you didn't print them out, you're not like well behind. But we're going to move out of chapter 3 into 4. So the tune-up course, which we've talked about briefly off and on Monday, when, heaven help us all, your mini exam 2s will be graded and returned to you. That requires everything in my life to go right, but I have a plan. We'll make it work. That way you have 3.5 days to decide whether or not you want to go to the tune-up course. The tune-up course is for students who have either struggled or been unsuccessful thus far in this course, and then you can transfer, and we'll talk about how there's no record that you were ever here, yada, 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 and you can go to Chem 1025. A couple of things to note. If you have taken Intro to Chem at UNF or at a different UNF-like school, FSU, UF, yada, any state system, this option is not going to work for you because you can't take the same class twice. However, you can come to me and we'll make a plan and we're all going to pass. That's the goal here. So, a couple of things. That's where we are. That is coming. If you are curious, you can email me. I will send you information. But next week, we will talk about it. I want to just give you the idea that it's coming. So your chemistry and life assignment, the first one is due next Wednesday. I can speak for myself. I only think 1 week in advance. Mini exam today, and I was going to write this up like, it's due in 2 weeks. And I was like, nope, it's due next week. It is due next week. If you do not remember this assignment, you need to write 300 words describing chemistry that you see. A couple of things. Those should be your photos, not Google. So please make a point that these are things that you actually saw, not that you Googled chemistry and life and then copied and pasted something from a Wikipedia article. So turn it in. We'll basically highlight the whole thing and give like 92 flags of copying, and then it'll tell me where you got it. It's not supposed to be hard. There is no late work, so if you miss the deadline, just hold on to it and submit it for the second one. There are a couple of people I think in here who have already done the whole course, like all 3 of them, so that's great. There are 3. I heard the door. So just make sure that you are looking for chemistry in life. I'm not asking for you to win a Nobel Prize. I'm literally asking for you to see something in your life that has, it can be far-reaching, but chemistry-esque.
Are we supposed to discuss anything specifically, like how do we, or why do we think it's chemistry, or what are we supposed to mention in paragraph?
The question is, what are we supposed to mention? What am I really asking for in your 300 words? What did you see? What makes it chemistry? Let's say that your job involved blowing things up with TNT. I don't know that any of you do this on the regular, but maybe you do. Who am I to judge? You could talk about, so in chapter 5, we'll talk about energy production. So you can talk about how the amount of TNT corresponds directly to how big of a boom you get. Give or take, that's mostly true. So that's really all I'm looking for. I prefer it to be chemistry related and not quite like I saw a pulley or a fulcrum or something that feels physics or something that is, I'm a biochemist, so I will cut you a pass if you're close in biochemistry to different types of things, other things. If you have questions about it, I'm happy to answer them. I would like to reiterate, this is not meant to be super hard. It's supposed to be, what did you see?
Stuff like cooking and nature.
Yeah, cooking. You guys are I don't want to call you my grown-ups, but like I teach freshmen mostly before this. So if you brew beer, or you distill spirits, or you make something that rises, all of that is fair game. If you're curious about beer and chemistry, there's some really great YouTube channels. My brother brews a lot of beer, and so we have long conversations about this, that, and the other, and why you would use this sugar versus that sugar. It's meant to be open-ended. The only goal is for you to say, oh my God, chemistry really is everywhere. That's it. I'm not asking for you to solve world hunger. I'm not asking for you to do anything crazy. Just that. Any other questions before we get started? Feels like someone is stuck out there, but I'm not. Oh, I just hallucinated that. I don't want anyone to get stuck on the other side of the door. Only one of them opens. We're still in the end of chapter 3. Chapter 4 will come after we finish chapter 3. It's okay. Now we're all on mostly sort of the same page. So we're at the very end of chapter 3. So today what we want to start to think about is, hold on, let me mark where the board is so that I'm mostly in the right space. So reaction yield. So at the midpoint of Monday's lecture, we looked at 2 breads, solid, plus 1 cheese. In this case, we'll call it liquid because it's molten. Gives you a grilled cheese sandwich, solid. So in this case, we started with 21 slices of bread, and I think 8 slices of cheese. And so therefore, based on, I don't know, sandwich math, we know that the limiting reactant is cheese. There's more bread than cheese. Therefore, cheese is the limiting reactant. And so the thing with determining limiting reactant, so all we're going to do right now is we're going to take a very tiny step beyond limiting reactants. This tiny step is not on mini exam 2, which is today. Limiting reactants definitely are. So I'm going to change a few vocabulary words, and that's about it. So we have this limiting reactant. And so we can figure out, if you made all the sandwiches you could, your yield, so 8 sandwiches, and I don't know how to spell this word, is the max. And I came up with that because if you used all the cheese, you could make 8 sandwiches. So that right now is our yield. But this is what we're going to start to call our theoretical yield. This is what you get if everything goes right. AKA, you didn't burn your grilled cheese, you didn't run out of propane if you're using your grill, you didn't, grilled cheese is pretty easy, you can't really mess this up. But the idea is, 8 is the max. Let's say you were having a dinner party and you're making grilled cheese sandwiches. So you're making sandwiches, and you've now used up all of your cheese, and you look at the platter and there's only 4 sandwiches left. This is 4 sandwiches. This is what you really got. And the idea with this is, what do you get at the end? So a lot of you may or may not be enrolled in lab. As we start to move forward, you're going to do a reaction, dry the product, and then you're going to weigh it. This is what I like to call data. And what I mean by that is it's not a calculation. It is exactly what you got. How long did it take you to get there? Hard to say. But at the end of the day, you only got 4 sandwiches. You should have gotten 8. So now we can figure out what percentage of the grilled cheese sandwiches that you could have made did you make. So we're going to erase parts of this. So now we can look at our percent yield. And this is what you actually got divided by your theoretical, multiplied by 100. So for your grilled cheese sandwiches, it's the 4 sandwiches you got, divided by the 8 you should have gotten, multiplied by 100, and that tells you 50%. Now, yields typically should be less than 100%. But it's possible, this falls apart with sandwiches, but it's possible that if you should have gotten 10 grams and you got 15, that you would have a 150% yield. That means something went wrong in your science. It doesn't mean great things have not happened, but the data is what the data is. So what you should have got, what you got divided by what you should have gotten, multiplied by 100. So as we think about yields, what questions do we have about percent yield before we look at the first chemistry example? So if you, I don't want to say scroll back in your notes, if you flip back 2 slides, so on slide 33, it should look a lot like what we see on 35. So in this case, we're basically going to, so instead, we're not going to rerun the first calculation. We'll do some examples in a second. So in this case, if our scientists collected only 7.7 grams, but if you look back at your calculation, what was their theoretical yield? If you look back at your notes, we did this calculation at the end of Monday's class. Yeah, so their theoretical is 8.03, and they got 7.70. Multiply that by 100, and we get 95.9%. This works a lot better when we don't have like 48 hours between them, just so we're all clear. So basically, the percent yield is the only part that we've moved forward on. Determining the theoretical yield is the same calculation that we did all day long on Monday. It is a quantity calculating the other quantity. So if you go from reactant to product, that conversion is considered the determination of the theoretical yield. What questions do we have about this calculation? It's pretty much division, so it's pretty simple. So in this case, we have a scientist who wants to make silver chloride from silver nitrate and magnesium chloride. After the scientist mixes 12.34 grams of magnesium chloride into a silver nitrate solution, they're able to collect 20.15 grams of silver chloride. What is the percent yield of this reaction? And then it tells you to assume the magnesium chloride is the limiting reactant. Now, it tells you that because we've just spent like 30 minutes, well not today, but we've spent a long time talking about like, always calculate the limiting reactant. Sometimes, by default, if we only give you one value, it is the limiting reactant. If we don't tell you anything about the other one, we're going to assume that there's a lot of it around. So in this case, what is the first thing that we need to do? Okay, find the theoretical yield. So in this case, we are going to, oh my God, take our 12.34 grams of magnesium chloride. We're going to convert that into moles of magnesium chloride. The molar mass of that is 95.21 grams of MgCl2. Now, what is the next step here? Do the ratio, the moles to moles. So for every 1 mole of magnesium chloride, there are 2 moles of silver chloride. Whoops. And then you need to convert back to grams. And in this case, for every 1 mole of AgCl, it weighs 143.22 grams. So when we plug this into our calculators, hopefully we should get 37.15 grams of silver chloride. Yeah,
How do you find that ratio, the 2 to 1?
great question. That ratio comes from the stoichiometric coefficient, so the big numbers up here. So in the event that you have a balanced chemical equation on the mini exam, you'll pull it directly from there. In the event that there isn't one, you would acquire them by balancing an equation. But this ratio here is from the equation. Great question. Other questions? So now we need to calculate the percent yield, which is that we got 20.15 grams divided by the expected 37.15 grams, multiplied by 100, and that gives us 54.24%. So what questions do we have about calculating percent yield? What questions do we have about limiting reactants? What questions do we have in general? Yeah?
Where will this stop being on the test today?
Here.
Okay.
It's just this part, which feels like it should. It's a very simple calculation. If things had gone, my plan was to get here on Monday, but we didn't, and that's okay. Other questions? In that case, I'll give you 5 or 6 minutes. So, adipic acid, which is H2C6H8O4, is used to produce nylon, and it's made from cyclohexane, which is C6H12, and O2. You start the reaction with 25 grams of cyclohexane and 98.2 grams of O2. What is the theoretical yield? In this case, it's asking about adipic acid. So please calculate the theoretical yield of adipic acid. And then if you obtain 33.5 grams, what is your percent yield? do have an extra one. It's a little rumpled from running around in my bag, but it is not mounted. Okay, so when we start this gives us two different quantities of the starting materials. So we have to identify the limiting reactant first. I'm going to pick, so when I look at these, I usually, whichever one I come to first in the question. That's just how I roll. You are welcome to try to guess. We all know if you pick first and do a reactant to reactant and it identifies the limiting reactant, you're good to go. 50-50 shot, which are fantastic odds for most things. But in this case, I am going to start with 25 grams of cyclohexane. So we're going to take our 25.0 grams of C6H12. We're going to convert that to moles. Using the molar mass of 84.18 grams and 1 mole of C6H12. From the balanced equation, we can see that there's 2 moles of C6H12, and there's 5 moles of O2. For every 1 mole of O2, it weighs 32.00 grams. You can plug that into your calculator, and hopefully you will identify 23.8 grams of O2. From here, can we identify the limiting reactant? Yes. We need 23.8 grams of O2. We have 98, so that's like a lot more. Therefore, cyclohexane is our limiting reactant. So then we can use the mass of cyclohexane to determine the theoretical yield. 25.0 grams of C6H12. That still weighs 84.18 grams in 1 mole. There's 2 moles of C6H12 for 2 moles of adipic acid, which I'm going to just annotate as AA for brevity. 1 mole of AA weighs 146.16 grams, which gives us a yield of 43.4 grams. Any questions about how I got to this point? Yes?
So I did that bottom part first and not the top part. So am I first supposed to find the grams of C6H12 to O2?
So what you did, so did you do the second calculation where you started with 98 grams of O2 and then converted to adipic acid?
I just did that.
So that is one way to kind of hope for the best. So you can, and there are a lot of instructors, Khan Academy, really a lot of people, teach limiting reactants as the easiest way to identify that is the one that makes the least product. So you could have said 98.2 grams of O2 converts to 32 grams in 1 mole. And there's 5 moles of O2 for every 2 moles of AA. 1 mole of AA gives you 146.16 grams of adipic acid. And I did not have that calculation, so let me use my calculator. So when I plug this in, what I got today is 179 grams. So the limiting reactant can be identified relatively simply by the one that makes the least product. And in the case of this question where it doesn't ask you about the excess reagent, this will get you the right answer. The problem is if it asks about the excess reagent, which is going to be on the mini exam, if you don't know how to calculate that, you'll have I don't know, like 9 minutes to review your notes. Or however many minutes it is. Yeah, 9-ish is about right. So in that case, that will get you to the right answer. In the case of excess, no, but this would work. Yeah?
Why do you think they calculate the limiting reactant before you do the problem?
So how would you determine the theoretical yield of adipic acid without identifying the limiting reactant? That's why.
Okay.
For the sole reason of, so some of these questions we're trying to think about other things. On the mini exam, both this one and anything else, it will ask you, it won't just like hop to the end and be like, what is this? It'll say like, using this, tell me about that. I'll try not to make you guess. This one has a lot of guessing involved, but that's not me. So the second part of that calculation asks what is the theoretical, what is the percent yield, which is 33.5 grams divided by 43.4 grams, multiplied by 100, and that gives you 77.2%. What questions do we have about this calculation? Yeah?
So there's, I mean, obviously, there's 25 grams of the cyclohexane and then 98.2 of the O2. So then, in what case would the cyclohexane not be the limiting reactant? It's less.
It's a good question. So the question is, if there is a less mass of one, can we basically make a shortcut to be like, less mass, probably the limiting reactant. So the only time that is substantially different is if the mass of one and the other is substantially different. So in this case, we have a mass here of about 80 and O2 is about 32. So if by chance they were flipped, where this had a mass of 80 grams per mole and this was about 20, it's possible that based on the molar masses, the mole ratios will be different. It's not a bad assumption to pick the one with the least mass. That's at least where I would probably start. Just because frankly, if you can cut any part of this calculation down, it makes life easier. So you can do it, you can make a best guess. But as far as I know, there isn't really any pattern for it's always the least mass or it's always the most mass or they use stoichiometric ratio. There might be patterns, but I've never seen them work. Other questions? Yeah?
The 1% yield, why did you divide by 43.4?
Because, yes. So this is what you got, and this is what you should have gotten based on the limiting reactant. Multiplied by 100. So for the next, 4 minutes, we'll start chapter 4. Yeah. We're trying to, this is more like a drive-by of chapter 4. Give us the idea of where we're going. So in chapter 4, we're going to start to think about reactions. Okay, we've been thinking about reactions. Thus far, I've said this thing mixes with that thing, and you get a product. And sometimes there are states, but sometimes it'll say, like, solid sodium chloride interacts with solid something else. Y'all, you can't put 2 solids in a beaker and hope for the best. Grilled cheese. You cannot put bread next to cheese and be like, grilled cheese. I mean, maybe you can. I can't. I do not have magical powers, if only. So the reality is 99% of chemical reactions occur in the presence of water. And not like water is sitting on the counter next to them, but they happen dissolved in water. So in this case, when we start to think about these reactions, we have what's called an aqueous reaction. This basically means dissolved in water. And when we start to think think about this, solvents and solutes, so a solvent is the substance that does the dissolving. In terms of most of our reactions, this is going to be water. Sometimes, if you have something that will not dissolve in water, maybe you dissolve it in a chemical solvent, which would be something like ethanol or cyclohexane, which comes as a liquid, or there are lots of other chemical components that come as a liquid. So it doesn't have to be water. For the purposes of Gen Chem 1, it's like always water, but outside of this, it's something else. So the solute is the thing that gets dissolved. So if you put sodium chloride, solid sodium chloride, in a glass of water, we know that it's going to dissolve. And what's going to happen is it's going to separate into its two ions, sodium plus and chloride minus. And so those two things are what is being dissolved. We also know that it is possible that sometimes things will not always dissolve. If you have a glass of water and you pour so much salt in there, you can get like a salty layer. And so that has to do with the solubility. So when we start to think about this, so we're going to move to the ability to say, what is happening in a beaker? So in lab, at some juncture, you'll take two liquids, squeeze them together, and see if a solid forms. Or you'll take a solid and drop it in certain liquids and see what happens. Or be like, nah, nothing happened. So what we're starting to do is to think about the science behind that. What do we see and how does it happen? It's really about all we have time for. So at this point, you can go ahead and put away everything but your non-